Good morning. Am I audible? Am I audible to you? Okay. So, in last class, I think we have finished that one, last chapter, that is hydraulic jump, isn't it? So, one more chapter is left to finish your syllabus, and that is a new topic, computational fluid dynamics. In short form, it is called as CFD. Okay, so it is called as CFD. So what is CFD? Let's see. So my screen is visible to all of you. Is this visible? Okay. First of all, let me unlock my meeting. It's my meeting gets locked automatically. Okay. So after some time, it's locked automatically. So is this visible? My screen is visible now. So okay, your last chapter is computational fluid dynamics. So I am referring some others PPT for you. Okay. So what is CFD? In a short, actually full form is computational fluid dynamics. In short, it is called as CFD. So it is the science of predicting fluid flow, heat transfer, mass transfer, chemical reaction, and other phenomenon by solving the mathematical equations which govern the process of which govern this process using a numerical process. Okay, so basically it is a numerical based process. Okay, the result of CFD analysis is relevant engineering data used in conceptual studies of new design, detailed project development, troubleshooting, redesign. So in engineering field, CFD can be used for studying new designs, for studying detailed product development, troubleshooting, and redesign a project. CFD analysis complements testing and experimentation, reduces the total effort required in the laboratory. Generally, CFD reduces the laboratory process. It is so base of the CFD. There are some fundamental mathematical equations which govern the CFD. Okay, and that one, first one is Navier-Stokes equation. I think all of you have got this equation, Navier-Stokes equation. Okay, so Navier-Stokes equation, which defines any single phase full fluid flow by some simplification, equation becomes, after simplification we will get this equation. Okay, where CFD is used. Generally, computational fluid mechanics can be used, fluid dynamics can be used in aerospace, automotive, biomedical, chemical processing, HVAC, hydraulics, marine, oil and gas, power generation, and sports. Where is CFD used? Aerospace, automotive, biomedical, chemical processing, hydraulics, marine, oil and gas, power generation, and sports. So in these areas, CFD can be applied. In marine structures, for the construction of marine structures or ship, aerospace means for movement of flight in air, all these require CFD. Float, lubricating over drill bit, flow around cooling towers. So CFD, how it works? Generally, CFD based on a mathematical model and a physical problem. Conservation of matter, momentum, and energy must be satisfied. Conservation of matter, momentum, and energy must be satisfied throughout the region of interest. Fluid properties are modeled empirically. Simplifying assumptions are made in order to make the problem trackable. Example, steady state, incompressible, inviscid, two-dimension. And it provides appropriate initial and boundary condition for the problem. CFD applies numerical methods called discretization to develop approximation of governing equation of fluid dynamics, fluid mechanics, and a fluid region to be studied. Governing differential equations, algebraic, the collection of cells is called the grid or mesh. The set of approximating equations are solved numerically. For the flow fill variable at each node or cell, the solution is post-process to extract quantities. Example, water flow over a tube bank. Physical system can be modeled. So the we have to model the we have to analyze the model in CFD. Okay. Mass generation. Geometry created or imported into preprocessor for meshing. Mesh is generated for the fluid region. A fine structured mesh is placed around cylinders to help resolve boundary layer flow. Unstructured mesh is used for remaining fluid areas and identify interfaces to which boundary conditions will be applied. Some boundary conditions we have to apply and we have to create some mesh boundary which gives us the boundary conditions of that problem. Okay. Advantages of CFD. So let's see what are the advantages. It is low cost, speed, ability to stimulate real conditions, So in low cost, using physical experiments and tests to get essential engineering data for design can be expensive. Computational stimulations are relatively inexpensive and costs are likely to decrease as computers become more powerful. Speed. CFD simulation can be executed in a short period of time. Quick turnaround means engineering data can be introduced early in the design process. So generally CFD uh, is a time consuming method. Okay, ability to simulate real condition. CFD provides the ability to theoretically simulate any physical condition, ability to simulate ideal condition, and comprehensive information. Computational fluid dynamics allows control over the physical process and provides the ability to isolate specific phenomena for study. Example, a heat transfer process can be idealized with adiabatic, constant heat flux, or constant temperature boundaries. Comprehensive information. Experiments only permit data to be extracted in a limited number of locations in the system. Pressure, temperature, heat flux, gases, etc. Limitations of CFD. So there are some limitations in the application of computational fluid dynamics, and these are physical models. CFD solutions rely upon physical models of real world processes, for example, turbulence, compressibility, chemistry, multiphase flow, etc. The solutions that are obtained through CFD can be as accurate as the physical models on which they are based. Numerical errors. Solving equations on a computer invariably introduces numerical errors. So generally computational fluid mechanics is a computer based model, isn't it? So it may have some errors, round off error, truncation error, okay, errors due to finite word size available in the computer, and there may be errors due to approximations in the numerical models. Round off errors will always exist, though they should be small in most cases. Next is truncation errors will go to zero as the grade. Just a minute. Hello? Truncation errors will go to zero as the grid is refined. So mass refinement is one way to deal with truncation error. Boundary conditions. So these are some limitations of CFD. So all of you have registered to that course, one CBCS course in Coursera. Everyone got the message. I think all of you have registered in Coursera course, isn't it? So there are some, I think it is for 7 weeks classes, isn't it? So you have to go through the videos, lectures, okay, and they provide some materials also. You have to study the material because it is a CBCS courses, so it is required. So you have to study that subject materials, okay. Week 1 classes, week 2 classes, isn't it? Have you go through the classes? Anyone in CBCS? Am I audible? Yes or no? So, okay, have you registered in Coursera course? So, let me share something, one video to you so that you can.
When you finally perfect.
So, I think it is audible to you.
Toy, or just confusing, or the greatest thing since the tone. Computational fluid dynamics, or CFD for short. This is a case where we use the computer to solve fluid dynamics problems. Why do we even need this? Why do we need fluid dynamics at all? Well, we live in a world of motion, and every movement that you make interacts with fluids. Walking down the corridor, air flows around you. Your body heats the air over your head, which then rises to the ceiling. A ship turning in a channel gets driven by the water flowing around the hull and the rudder. Every aspect of change in our world gets shaped by fluid dynamics. Given that pervasive presence, we need the ability to predict and control those fluid dynamics. CFD is one of the main tools that we use for this, and it's one of my favorite specialties. To talk about CFD, we first need to put it in context of all of the methods available for fluid dynamics analysis. To start off, we have analytical methods. This is basically some guy sitting at a blackboard trying to come up with a generalized equation. This only works for fairly simple, specialized equations, and it can be fairly laborious, so we don't see this too often. Then, at the other end of things, we have the experimental methods. We still see this quite a bit today. It's very, very accurate, but it's limited and it's very expensive. We have to build specialized facilities with high construction costs, and they have to be very highly calibrated and very carefully designed. We have to know what we're already testing for. So we can't really use them to explore new possibilities. We can really only test for situations that we already know about. And then we have the middle ground that's been created, computational methods. Now this can be just as accurate as experimental methods, but it can also be cheaper than experimental methods, and it gives us a lot more flexibility. It allows us to branch out into new unknown territories and gives us the ability to dive into new details. So it offers us a lot of the flexibility of analytical methods and a lot of the detailed accuracy of experimental methods. It's sort of a happy medium of both. Now you might think to yourself, hold on. Fluid dynamics has been around since the dawn of time, and mathematicians must have been working on this problem for years and decades and centuries. So why have they only now turned to computational methods? Why do we need computers to solve fluid dynamics problems? Haven't the mathematicians solved this already? Well, the basic answer to this is yes, they have been trying to solve this, and fluid dynamics are hard. They are very, very complicated. There's a story that I like to tell to explain this. I don't think this is actually true, but it makes a really fun story. There's a story that Albert Einstein one day sat down and tried to work out the generalized equations for fluid dynamics, all of the physics involved. In the end, he gave up because it was too complicated and went on to do special relativity. Now, like I said, I don't think that's true, but it gives you a sense for just how complicated the equations for fluid mechanics are. The full equation for fluid dynamics are what we call the Navier-Stokes equations. You can see them on your screen, and really that's just there to show you that it's a big, scary equation. And I really want to emphasize that there is no general analytical solution to this equation. You can look in every math textbook you find. I don't think I have ever yet seen one general solution to this differential equation that can work for every situation. So we have to turn to the computational method to find solutions that work for all sorts of situations. So what we're driving for here is some sort of generalized tool to solve Navier-Stokes equations. This is where the computational method came in. We said we can solve Navier-Stokes equations if we keep the geometry simple. So let's just keep it as a box. Okay, we can solve Navier-Stokes equations if it's just a box. As long as we know the conditions at all the boundaries, we can solve that. That's very, very good, because now we're saying that we have a generalized tool for this as long as we keep the geometry simple. And this is where we start combining that with the brute force capability of the computer. You take that idea of solving Navier-Stokes equations on a little tiny box. You divide your object into millions of tiny little boxes. We call these cells, and we call the whole thing a mesh. Each cell interacts with its neighbors. The engineer sets known values for the boundaries along the edges of the mesh. And then the computer uses the power of a brute force iteration to balance out all of the cells along the edges and in between all of the interactions. Now that is a lot of brute force solution to the equations. There's a lot of iteration that goes on, but that's okay. Computers are really good at brute force iteration. And that is the computational process. The really neat thing about this is that it's a generalized algorithm that we can apply to any geometry. It works for any situation. The same math just keeps working again and again and again. So let's break down some of the trade-offs that get involved here. First off, the good side of CFD. Computers are relatively cheap. You don't have to pay too much for that brute force power. You do get a lot of detail out of your CFD simulation, which is really good about answering not just what your values are, but why. It helps explain why the answer is good or why the answer is bad. It's very good for making corrections and improving upon your results. And it allows you to simulate your final product with real-world physics. You're not making approximations, you're not building models. You can simulate things as they actually are in the real world. And because of this, and because of the fact that CFD is a generalized solver, you can really tackle this without any prior knowledge of exactly what to expect. So that allows you to do a lot of optimization and exploration of your design. You don't have to reinvent the solution every single time. You don't have to reinvent the toolbox. You can just keep using the same tool for different designs. Well, that's a lovely sales pitch, but where's the bad end? I will say CFD has a lack of standardization. If you go to the experimental end of fluid dynamics analysis, there's a lot of standardization there, and that's very nice for having a lot of confidence in comparing different vendors for experimental testing. Not so much for CFD. We don't really have a lot of standardization. And so it's really hard to tell one vendor from the other. We don't come with labels saying good vendor, bad vendor. There's a lot more detail that you need to know about how to to pick one vendor for the other. And that does lead to a lot of misunderstanding. That does lead to a lot of misinterpretation, thinking that some vendors are bad. Another thing I do have to say is that CFD is an experimental analysis still. There's no working backwards. You can't say what your perfect solution should be and then ask me to find out what the exact wing shape is for that. I have to try wing shapes and just keep trying them until we get to your perfect solution. And then the other downside to CFD is the time cost. See, experimental methods can be just as expensive as CFD. They can be about equal depending on what your situation is, but CFD may take longer. Experimental methods, you can be done in a day. CFD, it takes quite a bit more time for this computer to crunch through all of the numbers. And so we actually look at much larger timescales for our project timeline. You have to start planning much farther in advance. One of the biggest questions I hear about CFD is it accurate? I'm really worried about the accuracy of CFD. I've heard so many bad things about it. Is CFD accurate? Yes. CFD is accurate. It can be. This goes a lot back to that problem of what I've said, that there are bad vendors out there. And I'm sorry, we don't come with labels saying that we're good or bad. But yes, CFD can be very accurate when done with a good vendor. So what kind of accuracy can you get out of CFD? You as the client actually get to decide how much accuracy you want to pay for. The higher accuracy you want, the more time we have to spend with the computer crunching the numbers. So what can you actually achieve? Plus or minus 10%, that's very easy to achieve for most CFD problems. In general, for industrial CFD, you should expect plus or minus 5%. I would say that's a typical requirement for a CFD simulation. Plus or minus 2%, that's excellent for a CFD simulation. And that is actually on the level of accuracy that you will get with an experimental setup as well. DMS has actually achieved that accuracy in some simulations. So it is achievable, and if you're concerned about it, ask for it, write it into your contract. That can be done. How do you actually get a good CFD vendor? You ask for two different things. You ask them to prove their accuracy with two separate things. Number one, validation studies and mesh independent studies. In lack of any sort of standardization, these are the two things that vendors do to prove that they are good at CFD. A validation study is where they take an experimental study, they duplicate it in CFD and compare their CFD results to the experiment and see how far off they are. They should be able to show you that comparison. A mesh independent study is something that you should expect to be done for every single CFD project. It is a study of varying the mesh size to make sure that the actual sizing of the cells in your mesh doesn't change the quality of your simulation. So this was a very quick, high-level introduction to CFD. The basic takeaways that you should have from this are that CFD has its place. It's not going to replace experimental and analytical methods. It's just another tool in the toolbox. And as part of a new tool in the toolbox, it can either be a major help or a major burden. The key is to understand the tool, understand its limits, understand what to ask for from your vendors. And the major thing to ask for from your vendors is I would say that your CFD operator has to be a fluids expert first. Don't just get somebody that's a software vendor that sells the software. Get somebody that has a background in fluid mechanics. And when it really comes down to it, you really should also be demanding CFD accuracy. Don't let them tell you about the software. Don't let them tell you about how fancy it is and how powerful their computers are and all of that. That's their thing, okay? That is their burden to ensure that they have efficient execution. Your burden and the part that you care about is to ensure that you have accuracy. So demand accuracy, demand that they prove accuracy. And that is for validation studies and mesh independent studies. And if you do those two things, that's the closest thing you're going to have to a little label that says good CFD vendor. And you really are going to start seeing evidence that yes, CFD is accurate, reliable, and it is going to be a major help to your organization. Thanks very much. I'm Nick, the Naval Architect.
Hi there. I invite you to apply for the PG Diploma program in Data Science by IIIT Bangalore in collaboration with UpGrad. A few
So I think you have got a little idea about CFD. So in details, it is not required. When you are going for after graduation, you are going for further study, then you will get about CFDs in detail. Okay. So for today, I think I I should have ended this class. Okay, don't go. Let me take a screenshot of your attendance. Okay, done. So thank you all of you. I will share notes shortly before exam.